Hey all you cool cats and kittens. Today we're going to learn about flexural design, and this means we are talking about the design of beams. Is this going to work? Hold on. Okay. We're talking about beams. Going to go through some of the things we went through with flexural theory and how those have been incorporated into flexural design. First, we're going to talk about where we're talking about in the manual. If you go to chapter B, is whether or not local buckling will occur. And this is on page, let me go there. B4, no, this is slightly out of date, but if I go to table B4.1a, 16.1-17, you'll see we're talking about a width to thickness ratio, right? Our how wide our flange is versus how thick it is, or how tall our web is versus how thick it is. But notice this talks about axial compression. This is what we used to determine whether or not we needed to check for local buckling for just axial compression or columns. Now we've moved into flexure. So table B4.1b. Flexure. Okay, make sure if you're designing a beam, you go to table 4.1b and not 4.1a. Okay. Then chapter F is where we have all of our design equations for flexure. Right, that's back in the spec. And finally, our design charts and tables are part 3. Which starts on page 3-1. Right, our little tab that says beam. Okay? So let's start off talking about whether or not something needs to be checked for local buckling and whether or not local buckling will occur. So we're going to be talking about 3 different numbers here. My lambda, which is my width to thickness ratio. And again, that's how wide my flange is to how thick it is, or how tall my web is to how thick it is. Then lambda p, which is my limiting ratio, limiting width to thickness ratio, on whether an element being a web, a flange, a stem, limiting ratio to determine if an element is compact or non-compact. And then lambda r, which is my limiting ratio for non-compact, compact versus slender. And we're going to define what those mean. Basically what they mean, not necessarily the definition, but what being labeled compact, non-compact, or slender means in terms of how the element acts within the cross-section when it's subject to flexure. So compact, non-compact, or slender. An element is one of those three things. If it's not obvious, compact, less likely, or no local buckling, slender, more likely, non-compact is in the middle. So if my width to thickness ratio is greater, let me make sure. Yeah, it's the other way around, wouldn't you think? I need to fix these, right? If my width to thickness ratio is less than lambda p, then my element is, right? That means it's a lot thicker compared, a lower one means you either have a smaller width or a bigger thickness. Then my element is compact. And that means that I reach my plastic moment, MP, before any local buckling occurs. So if I have a compact flange, my cross-section is going to reach the plastic moment. It's going to be a fully yielded cross-section before that flange buckles. If yeah, okay. If I'm between the two ratios, then my element is non-compact. And that means that I'm actually going to have some local buckling, but it's going to be in the inelastic range. So some yielding has started to occur. Some yielding has started to occur within my cross-section, but I haven't fully yielded the entire cross-section. This corresponds to a moment less than my plastic moment, but greater than 70% of my plastic moment. This is the inelastic range. as defined previously in flexural theory. Yielding begins to occur within the cross section when the applied moment is 70% of the plastic moment. So I defined compact and non-compact. Obviously my last thing is if my lambda is greater than lambda r, then I have a slender element. This one you might be able to figure out. Local buckling occurs in the elastic range. In elastic range, not, yeah, I'll make sure there's a big. That means my moment is less than 70% of my plastic moment. Right? Think of the lambda as like a slenderness ratio. Right? If it's a small slenderness ratio, you're not likely to have buckling before you reach your plastic moment. As it gets bigger, you're more likely to have local buckling. And whether or not it occurs in the inelastic range and the elastic range is what those ratios are for. Okay? This is the chart corresponding to that right? This is my compact section. This, because below here, I'm at my plastic moment. This is my non-compact section. Because I'm at 70%, meaning this has this is inelastic. It means part of the cross section has yielded, but not all of it, is what inelastic means. And finally, as I increase my lambda, I get slender elements. Because we're in the elastic range. All right. fully yielded cross section. Partially yielded cross section. Not yielded. Nothing's yielded. So compact, fully yielded cross section, so you're not going to buckle before you yield. Non-compact, there's some yielding going on, but you haven't reached full yield of the entire cross section, so you're not at a plastic moment. Slender, elastic means nothing has yielded. Okay? Nope. Next slide. So if I go look at section F1, this is back in the spec. How do we design for flexure? Page 16.1-44 is the beginning of chapter F. Flip the page, general provisions, 16.1-46. Your design strength. Moment is phi times your nominal moment capacity. Mn is your nominal moment capacity. Multiply it by a phi factor, phi b for bending. Phi b is 0.9. And like I said, Mn is your nominal design. Your nominal moment strength. There was also equation F1-1 is our modification factor for non-uniform moments. lateral torsional buckling modification factor for non-uniform moment diagrams. I know we're all excited to do moment diagrams back when we were in structural analysis. And now you know why you had to learn them before you came to this class. If we went back in our notes, we sort of briefly mentioned this, that we were assuming a CB of 1 for some of our theory. And now I'm going to talk about why we have to modify our non-uniform moments. Non-uniform moment diagrams. Basically, if you were to look at a moment diagram, it is not usually, right? If this is, it's not usually a straight line, right? Usually looks something like that. Right? If you have a bunch of distributed load, it would have curves like that, parabolas. You're not going to have a uniform moment across the entire beam length. This is along the length, right? The moment varies along the length of the beam. So, because of that, why do we need to design for the very worst? When that might only be happening for a very short amount of time. A very short amount of length. Why should we design an entire long beam for just that one little moment? So we modify, this is for lateral torsional buckling only. We get to modify our moment because of that. Because lateral torsional buckling assumes that you have the same load and the same moment along the length, which you don't. So, I am going to look at 4 different points between bracings. Now these would be braces against lateral torsional buckling. I feel like we should look at what lateral torsional buckling looks like. Actually, let me see. Here we go. Lateral torsional buckling. It means right, we're talking about right here. All right, lateral torsional buckling. Is if your top flange is moving laterally, right? Top flange is moving laterally, and it's also your entire cross section is twisting, torsion. Oh, that looks terrible. Yeah. So if we want to brace against lateral torsional buckling, the easiest thing to do is hold on to my top flange so it doesn't get its nose out of joint, right? It doesn't displace laterally. So that would be what we mean when we're bracing against lateral torsional buckling. For example, and I think I've said this before, if you have a slab, if your top flange is continuously connected to a floor slab, then you are continuously braced against lateral torsional buckling. So, if I'm looking at the moment between the variation of my moment between my braces, I get to look at my maximum moment and then divide it into 4 so that I have A, B, and C. LB over 4. My braced length, LB, over 4. So what would that look like? If I have the purpose of the modification factor is to make my is to equate what I would have as the I'll write it down. The purpose of the modification factor it creates a uniform, golly gee willikers, if I could write, a uniform moment diagram we want a uniform moment diagram because a uniform moment means you have uniform compressive stress, which that compressive stress, which within the compression flange, is what's causing that buckling in your top flange, causing it to laterally buckle. Right? Let's write that down. I'm not going to put uniform compressive stress, which is what's causing the buckling, leading to lateral torsional buckling. I want to take an arbitrary moment and make it look like it's uniform along the entire length. Right? If I have a CB of 1, that means I have a uniform moment along the length between my braces. And then these are just different examples of if I have half a moment on one side and a full moment on the other, I would divide my maximum moment, which would be M, by 1.25 to create a uniform moment along the length. So let's do an example. I'm going to do one. These are two different bracings. Same moment diagram, but different bracings. Let's say my maximum moment here is 1 kip foot. Okay? If I divide my length by 4, I'm going to use similar triangles, right? Going to assume stuff. Right? If my entire length between my braces, LB, divided by 4, maximum in the center is 1 kip foot. A quarter length would be half a kip foot. And on the other side, half a kip foot. Right? So, what's my maximum moment? One kip foot. A, this would be A, right? Half a kip foot. And B, I lied, it's 1 kip foot because it's right there in the middle. And MC is half kip foot. This is C. All right, I'm going back and looking at this right here. My CB, my LTB modification factor is 12.5 times my M max divided by 2.5 M max plus 3 times my moment at A plus 4 times my moment at B plus 3 times my moment at C. So if I use these values for M max, MA, MB, and MC, what value do you get? I got a value of about 1.32. that means my uniform moment that I need to design for equivalent is my M max over my CB. Or my equivalent uniform, I guess. Gee willikers. Equivalent. So if I want to take this moment diagram and make it an equivalent moment diagram, I divide my maximum moment by my CB factor. Go away. So 1 divided by 1.32. I get, what, 0.76. So when I'm designing for, and hoping that I don't have lateral torsional buckling, I only have to design for a moment of 0.76 kip feet instead of the full 1 kip foot. Because I'm not going to have equal compression in the compressive flange or whatever is up top, where you or whichever you have the compression in. I'm not going to have equal compressive stress along the length. So I'm not going to have the likelihood of it to buckle the entire length. So I only have to design for 0.76. Now, 0.76 kip feet. Now, let's say I have the same beam simply supported with my point load. And now I have this bracing. I've actually added a bracing here right at my maximum moment. So I only have to look at this portion of the length of the beam. It would be the same on the second half. Now, my B, right, halfway along my length is half a kip foot. My quarter point, A, is a quarter kip feet. And my 3/4 length is 3/4 kip feet. So if I do the same values, M max, I still have a maximum moment of 1 kip feet, but my MA is now only a quarter kip feet. MB is a half kip foot, and MC is 3/4 kip foot. So what value does that give me for my CB? I got a value of 1.67. So my equivalent moment that I have to design for is 1 kip foot divided by 1.67. Like my maximum is still the same, right? But now I only have to design for a uniform distributed moment of 0.6 kip feet. 1 divided by 1.67. I hope you all followed along with that. That is definitely maybe a little funny to wrap your head around, but hopefully you followed along with the calculations. And please remember to ask questions. So, right, it makes sense. If now, if you add a brace where you have your maximum moment, you're only gonna have to design for a lower moment than if you didn't have a brace there. Earlier when we talked about lateral bracing, or lateral torsional buckling, we talked about how, right, let's figure out what this diagram is. This is our braced length. And this is my moment, my nominal moment. This right here is my limiting moment, my plastic moment. This is my moment defining between, this is my moment between inelastic and elastic. I don't remember what this one's called. It's the moment between inelastic and elastic buckling. Right? My length, LP and LR. Alright, this all looks kind of familiar talking about local buckling and lateral torsional buckling. You look at limits. You look at a limiting width to thickness ratio or a limiting length. And if my length is less than LP, I have plastic yielding. If it's between LP and LR, I'm going to have inelastic lateral torsional buckling, meaning it will fail. It can fail with inelastic lateral torsional buckling. It can fail with lateral torsional buckling with yielding already beginning to occur within the cross section. And if I'm greater than LR, elastic lateral torsional buckling. Now this is what we made the other day when we were doing flexural theory. Now, how's my stomach if you heard that? That was all assuming I had a uniform moment distribution along the cross section, along the length of the beam, I mean. But what happens if I don't? All right, let's add our labels here. LB, LP, LR, MR, MP. Well, good news was I have a little bit more to deal with, to play with, right? But I'm still limited by, yep, this curve gets bumped out, which means if I just took the length, I can have a bigger length, a bigger unbraced length before lateral torsional buckling comes into effect. But I'm still limited by my plastic moment, right? I could have this is for CB greater than 1. I can have a longer length, right? If I'm in here somewhere, if this is my length of my beam, on my unbraced length, if it was a uniformly distributed moment diagram, meaning my compressive stress was the same along the entire length of the beam, I would have buckling before I reached that plastic moment. But if I have a different distribution and my CB is greater than 1, I will reach my plastic moment before lateral torsional buckling. That is why it is actually conservative to assume your CB is equal to 1. I'm going to stop this right here.